So take a look at the take-home quiz, please. Oh, hang on, let's pause. Number one, I've given you 2 point charges, and by point charges, I mean circular charges, and really what I'm saying to you is, hey, what can I ask if you have 2 charges? Weil, what's A asking me to find?
The magnitude of electrical force.
Yeah, electrical force. I didn't ask for the direction. For the direction, I'd have to tell you which charge we were talking about, because I think in this case, each charge is feeling a force in a different direction, so I'd have to tell you. I just said the magnitude of the force. Tato, what's B asking me to find? Magnitude and direction. So I can give you 2 charges and say find the force between them. I can give you 2 charges and the location and say find the net electric field, the overlapping electric field at that location. Sarah, what's C asking me to find? Did it say electric potential or electric potential energy? Which is not the same as electric potential energy. So C says find that. Could also have asked you to find the electric potential energy that these 2 charges have in that location. I did not, but I could have. Number 2. What's number 2 asking me to find, Alec?
Work.
How much work? I think I'm going to go change in potential plus change in kinetic. Now, it says moving an electron from an extremely large distance away. What's that code for? What do I really mean by that statement? Where are we starting? Infinity, which makes this question a lot easier. Makes this question a lot easier. Turn the page! Oh, by the way, I would probably, for number 2, DULP as well. Number 3, a proton initially at rest will have, Jaden, what's number 3 asking me to find?
Speed.
Is it asking how much work? So, no. Which way is that proton going to move? To the left or to the right? And how do you know?
It's gonna move to the right.
How do you know it's going to move to the right? Because like charges, and that 5.5 is fixed, it's glued to the page, so that proton is going to take off pew, to the right. Is there a change in height? Is there a change in speed? Is there yucky curvy force? I think I know how I would solve this one. Now this one you're going to be asked to find V final. Okay, so it's conservation of energy, G. I need to talk about number 4 because it's a typo. In number 4, Zach, in the question, how big is the charge right there? In the question, how big did I tell you the charge was in the type?
-5.5.
And in the diagram?
-5.
So can you do me a favor? Can you add a 0.5 to the diagram? It is negative 5.5. Sorry, I was writing in a hurry. Now, in this one, we have the electron starting out 5 meters away, moving towards that negative charge. I guess as it moves towards that negative charge, it's going to slow down, because like charges repel. Where will it come to a stop? Zach, is this question asking me how much work? I don't know. Oh, is there a change in height? Is there a change in speed? Is there a yucky curvy path? I would solve this with conservation of energy, G, as well. So I opened up this lesson by saying, look, is there a situation where our electric field and voltage equations don't have an R on the bottom and we don't have these yucky curvy situations? The answer is there is such a situation. I spend actually 3 days looking at what we call parallel plates. What do I mean by parallel plates? We know what the word parallel means. I want you to imagine we have 2 metal plates. Look up. Something like these 2 rulers. Okay? They don't have to be quite this long. So I wrote here another important voltage problem, in fact, a useful tool in electricity, is parallel metal plates. Large, flat metal plates, and by large, I just mean, Ira, large on the atomic scale. So, not a few millimeters long, but 5 or 6 centimeters long, longer, also fine. So you can imagine something like this, are charged up, and the plates are a distance apart. Doesn't have to be a big distance, maybe not quite 3 or 4 meters apart, but a few centimeters apart, or even a few millimeters apart if you want to get closer. What we're going to do, Linnea, is we're going to charge them up with a power supply. We have a battery here. You might recall from your Science 9 that the long line in the battery is the positive end. The short line is the negative end. This is not a circuit because it's not connected right there, and so charge can't flow. But what will happen is one side of the plates, one plate will have a excess of positives, and the other plate will have an excess of negatives. And that's really, 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 really useful. And if the metal plates are very large, and again, by very large, Gurjot, I'm just talking on the atomic scale, so really only a few centimeters long, then here is the key idea. The voltage varies directly with the distance from the plates. That seems like, huh? And it's so easy, even you can do it. Here's what, that came out wrong. Here's what I mean. So, Ange, look up. Here's a picture of parallel plates. How big is the battery? How many volts is the battery that we've hooked it up to, Ange? Just read it to me. Loud and proud again. And what's the distance between the plates? It says this distance here is 5 centimeters. Here is the nice thing about voltage between plates. Remember I said that voltage was kind of like height? Between parallel plates, it's a nice linear measurement. And how big is the distance between the plates? How big is the voltage source? Each centimeter, you're going to travel through 100 volts. In other words, if I go from the bottom and I travel 1 centimeter, and if I had a voltmeter, it would measure a difference of 100 volts between the top and the bottom of that little line right there. If I travel 3 centimeters, it will measure a difference of 300 volts in this area right here. If I travel 4 centimeters, it will measure a distance of 400 volts in that area right there. The voltage change between parallel plates is nice, it's linear, or, as I said, it varies directly. That's the first nice thing. Suppose we were to graph this data, voltage versus distance. What would the slope tell us? Now remember, before Christmas, I taught you graphing tricks. What was the trick for slope? What did we do if we wanted to figure out what the slope was telling us? If we hadn't seen the graph before, what did we do so that we didn't have to memorize every graph under the sun? Do you remember? Because slope is what over what? You say over? That means divide. So the first thing that I would probably try is dividing voltage by distance. I don't exactly recognize that equation. Now, it is on your formula sheet. We haven't looked at it yet, though. So now what I would do is I would go to the units. What do I measure distance in? Meters. What do I measure volts in? We defined it last day as something per something. And if you forget, if you look at our definition of volts, which I think is the first voltage equation, I think it only has 2 variables in it, something over something. Or is it the second one? I don't know what order I put them on your sheet in.
Joules per kilo.
Oh, so this is joules. Look up, look up, look up, look up, look up, look up. I'm not going to write this because that looks like millicoulombs. I'll put a dot between them so I know that's meter coulombs. We're running out of letters in our English language. Oh, and I don't want to write it as cm because I'll think that's centimeters. So anyways. Okay. Now, everybody right now, circle those 2. What's joules a measure of? Energy or work. Is there an equation? Oh, what's meters a measure of? Is there an equation that has work and distance in it? There is. So, oh, are you telling me joules per meter is force? Just a little arrow pointing there. What do I measure force in, Tato? So are you telling me this is newtons per coulomb? What do I measure in newtons per coulomb? It's on your sheet. I'm willing to bet also in this unit you have an equation that has a force over a charge in it. I'll bet you. What is it? if we were to graph volts per meter, the slope tells us the electric field, which gives us another way to calculate electric field. Do you remember at the very beginning of this unit, I said to you, Chang, gravitational field had 2 units, meters per second squared and newtons per kilogram, and I gave you electric field, newtons per coulomb, and I said it also has 2 units. Today, we're going to learn another way to think about electric field. So we've just noticed for parallel plates, there's a constant ratio of voltage drop over distance, and this ratio, this slope, is the electric field, which means in the box down here, we can write a new equation for electric field. It's the voltage divided by the distance that the plates are apart. Or how far you've traveled between the plates, whatever distance we're talking about there. Now you'll notice, Zach, I didn't use R for distance, even though R is also measured in meters. Why not? I'm trying to help you realize that you don't use this equation for round point charges. You only use this equation when there is parallel plates. But this also gives us another units for electric field. So we already said electric field was newtons per coulomb, but I guess it's also volts per meter. And we just did the derivation right there. A volt is a joule per coulomb, but then we combined the joules and the meters and recognized, hey, that was force. So here's what this gives us then. This gives us a uniform or constant electric field. Where is the electric field constant? Between parallel plates. And our math Tato just got way nicer. We've also invented television, although you don't know that yet. So, example 2 says, find the electric field and direction inside the plates. We now have 3 ways to calculate electric field. We have electric field is KQ over R squared. Electric field is F over Q. And today we have electric field. Did I say change on your formula sheet? Did I say change in voltage over D?
Yeah.
Because you do have to go through a certain, there is a final minus initial change in voltage that you're doing just in figuring out how many volts you travel through. Which one am I going to use for the question that we're doing? Do you see round point charges, little circular charges? I'm not going to use the one with the R in it. Did they give me a voltage? Did they give me a distance? I'm going to use this one. Now, I have to be honest. Probably on the test, I would not only give you, don't write this down, this distance, I would also give you that distance. I would tell you how long the plates were, and if this was multiple choice, that would be an answer to pick from, even though you don't need it. That's just to give you one more wrong answer to pick from. So, Tato, what's our new equation for electric field? Technically, the change in voltage. So if I travel from here to here, or from here to here, I didn't specify which way we're going, what's our change in voltage? How many volts are we traveling through? Yeah, you could say negative or positive. This is why I'm sloppy with the change in. I just really look at how many volts there are between the plates. And what's the distance between the plates? 0.03. 3 centimeters, convert it to meters. What's the electric field between those plates? And you could say newtons per coulomb. I would give you full marks. But since I used voltage and distance, I'll write my units as volts per meter. Oh, don't turn the page yet, Weil. We don't have the direction. How do I figure out the direction of electric field? Well, Weil, we imagine a little positive charge sitting right there, and we ask, which way would it want to move? Well, it would want to move away from positive towards negative. Is that going to be to the left or to the right, Weil? Because this is more positive than that. before you turn the page, I would get exactly the same answer if instead of 225 and 0, I had 325 and 100 volts. The change in voltage is still the same, 225. And even though these are both positive, this is more positive. I guarantee a positive charge would still move to the right. Now you can turn the page. Example 3 says, how does the electric field at the point X compare with the electric field at point Y? You know what? Let's find the electric field at point X. That's going to be the voltage at point X divided by the distance in point X. So, Josh, how many volts from here to here? 500 volts. That's my delta V. That's my change in voltage. What's my distance from here to here?
5 centimeters.
So what's each centimeter that I travel, what's the change in voltage that I'll go through?
100.
So what's my distance right here?
2 centimeters.
So it's going to be over 0.02. How many volts will I have traveled through starting on the left and ending at X?
200.
Yep. What's the electric field at that location? I think 10,000 newtons per coulomb. Direction from positive to negative, I think, to the right. Mobeen, let's also look at the electric field at location Y. That's going to be the voltage at Y divided by the distance at Y. And it looks like this line they're wanting me to look at, this path is this one right here. Mobeen, how many centimeters long? What's the distance here?
3 centimeters.
Convert it to meters for me, please.
0.02.
I agree. How many volts will I travel through traveling on this little arrow right here?
300.
Do I get the same answer? I do? You don't yet realize how nice that is. But it means that the electric field there, anywhere inside there, the electric field will give us the same answer, which gives us the ability to do some shortcuts and some much nicer math. Stay where you are. I forgot to talk about television. This picture here. Supposing I had an electron traveling this way. Right in here, which way will it get bent? What if I bump up the voltage even more? Will it get bent more or less? More. What if I reduce the voltage? What if I flip the voltage? What if I bump it up and flip it? And what we've just invented is the ability to hit an electron against any location of a television screen that we want to. And we make a dot, we now call them pixels, on an old black and white TV glow for a split second. And since we can make a dot glow, if we do that with several thousand dots, our eyes will see a picture. That's television. It's very low tech. That's not how flat screens work. But if you have one of the old televisions that when you look at it from the side, the back has a big thing sticking out like that, okay? That's actually 2 sets of parallel plates. It's an electron gun. It's called the cathode ray tube. That's how a television works. It's really cool. I mean, flat screens are great, but until flat screens came along, I was actually teaching kids how their TVs worked, which they thought was pretty neat. Now, none of your TVs, your iPods or iPhones, none of them work that way. It says, explain your answer using principles of physics. Well, Bean, I think we proved it, so I'm good with that. So it says, how does the electric field at point X compare with the electric field at point Y? We already figured out that for situation A, electric field at X equals the electric field at Y, which means the electric field is constant. Mobeen and Josh and I just proved that. What about situation B? How do I find the electric field from round circular point charges? There's an equation for it. Here equals KQ over R squared. Jaden, at location X and at location Y, is little k the same? Well, yeah, that's a constant. Is the charge the same? Yeah, the big planet hasn't changed. At location X and location Y, is R the same? So is the electric field the same? No. Since R at X is not equal to R at Y, the electric field at X, is the electric field at location X bigger, smaller, or the same size as at Y? The electric field. In fact, since it's more than twice as close, it's more than 4 times as strong. Right? The squared thing. It says explain your answer using principles of physics. I would argue we just did up there. So what's the first equation you have for electric field on your formula sheet? So we can rewrite that one like this, yes? In fact, we said this was the equivalent of little m, little g from gravity. Wait, no now. Wait, no now. But how have we just rewritten electric field? So here is yet another equation for the force on a charge between 2 plates. Not on your formula sheet. You can put it on your blue sheet if you want to, but it doesn't go on your yellow one. It's hidden in your yellow one because it's a combination of this equation rewritten, and I did give you this equation on your yellow formula sheet. Now we're going to spend some more time looking at that. So a little technical comment if we turn the page. We can see why electric field is constant inside plates and why it varies with distance from a point charge if we graph it. So for plates, the voltage is linear because as an equation, electric field, I said the voltage is linear, the electric field is linear, is just V over D, and there's no exponents and no yuckiness. But here, we have a 1 over R graph. This is a reciprocal of a radius. You're going to get a curve. You get a constantly changing slope. So I wrote here a technical comment for all of our electricity concepts so far. Force, field, potential energy. I've tried to give you, Chang, a hook to hang it on with gravity. I've tried to give you a gravitational analogy. What's our gravitational analogy for voltage? Well, voltage, also called potential, is the amount of energy per charge. That's similar to gravity potential, which is the amount of energy per mass. And if I take the mgh and divide it by m, this is gravity potential, which is the constant gravitational field times the height. So I think of voltage as equivalent to height. It's not quite the same as height. It's a constant times height. But actually, I said this then. mgh is an awful lot like qv. The only reason that the v doesn't have a constant like little g in front of it is because of how we defined the units in the first place for voltage. What's your homework? Short lesson. Oh, hang on, I'm not done yet, sorry. Almost done. With this analogy, we can think of parallel plate voltage as a steady sloping mountain and point charge voltage as a curving slope that starts out steep and gets shallower, if you really, really want to. And the electric field is just the slope of that voltage hill. So you can sort of think of voltage as height. Patrick, you gonna make it? You're having a little trouble there.
Yeah.
Okay. Okay. Now, what's your homework? Here's what I assigned my block E's. 1/5/6. What's number 4 asking me to find?
Force.
Force. So I would start out by saying for number 4, electric field is that, which means force is that, and electric field between two plate charges is that. Between two plates, charged plates, is that. So you get a new equation for force. This is the force on a charge anywhere in this area. And you can see it's a much prettier equation. It doesn't have squares and reciprocals and all that stuff. I promised you, Alec, the math would get nicer. It's about to get nicer. Alec, what's number 5 asked me to find?
The work.
I can use this because the force between plates is constant. How do I know that it's constant? That distance is the distance between the plates, which isn't changing. That voltage is the voltage that the plates are hooked up to, which isn't changing. That little Q is the charge inside here, which isn't changing, which means you have a constant force. And oh my goodness, I don't need to go change in potential plus change in kinetic, final minus initial. I can use force times distance finally again at long last between plates. Number 6 you can try. Number 8 you can try.